it's gone. Okay. Never mind. Okay. Hello, everyone, and very welcome to this very first meetup meeting of the Data Engineers London. Yay! Before we started this group, we were discussing it, and we thought, oh, if 5 people show up, we'll count this as a success. So I think we've kind of smashed that target. So thank you all for coming tonight. I'd like to start by saying thank you to our sponsor tonight, WeShape, who have provided the beers and the pizzas and the space as well. Yeah, Pat and Jamie are going to be around here if you want to say hi to them at some point and find out what it's like to work at WeShape. So I guess I'll start by a little intro and background about me, about the group, about why we're all here tonight. So hi, my name is Anna. I've met some of you tonight. Turns out I'm wearing the same sweater as in the photo, but I swear that was not planned. I graduated with a degree in biochemistry, and very quickly while I was still doing biochemistry, I realized I had absolutely no interest in pursuing that career. So I switched into technology, so working with data for 5 years. I was working in banking with a very proprietary database. And I realized I really, really enjoyed it, but it was very narrow, it was very proprietary, and I knew if I would never be able to move on with this. So hence why, oh, no, sorry. Let me go back. So I kind of thought that, I would be in this job forever. So hence why I made the switch, and I worked in 2 startups over the last 2 years. And I've learned a lot. I'm not in startups anymore, I've gone back to corporate. But here's just a snapshot of the technologies that I got to work with in those 2 years. So I work with AWS, I'm currently working with GCP, Kafka, Postgres, Airflow, dbt, Snowflake, and that's just working 3 different places over the last 2 years. So as you can see, the breadth and depth of the data engineering profession. And I like going to meetups, but what I found that a lot of it was kind of focused towards AI and towards MLOps and towards DevOps engineers, but I didn't meet fellow data engineers that I could talk with and I could interact with, who shared my interests, who shared my maybe career path, shared the technologies that I work with. So I tried looking up meetups, couldn't find any active ones, so I started my own. And here we are tonight. So what I'd like to do, I'd like to talk a bit for the future, what I'd like this group to become. And I'd like this to become a knowledge exchange for ideas and inspiration for fellow data engineers or people who are interested in entering the profession, or those who are and would like to up their knowledge. So I'd like this group to become an interchange for that. I'd love to build a community of data engineers and fellow people who are interested in the data engineering field. I'd like people to support each other and to help each other out and to spread knowledge about the cool things that you've learned, basically what you get to see in other meetups. I'd love to grow the group, but as you can see, I think we've already smashed the target for tonight, so I think we're starting off pretty well. And I guess since this is the first meetup, I thought this would be a good opportunity to kind of talk about the data explosion that happened in the 90s with the start of the internet, which ultimately led to the rise of data engineering as a profession. So the big data explosion happened, well, people were kind of discussing, the generation of data and human-generated data, so going back to the 40s, but I think it's safe to say that the internet has really, sped that process up in terms of the amount of data we generate nowadays. So if you think about social media, the popularity of online shopping, mobile apps, most of you probably used an app to get here tonight to find this group meetup. So you can imagine every time you click, every time you interact with these technologies, the amount of data that you're generating and the amount of data that is being stored. And behind that is some poor data engineering trying to figure out how to not lose that data and to make it available to the analysts to be able to gain some sort of knowledge from it. So the first time they hear someone actually say big data was in this 1997 paper, application control demand paging for out-of-core visualization. I have no idea what that means. By NASA researchers Michael Cox and David Ellsworth. But what they talk about is data sets are generally quite large, and keep in mind this is just 1997, just 1977. Data sets are generally quite large, taxing the capabilities of main memory, local disk, and even remote disk. We call this problem of big data. And in 1998, you kind of begin to see people talking about the data that's being generated by the internet and kind of becoming not worried, but kind of realizing the extent of infrastructure, of the ability to, trying to predict the amount of traffic that's going through the internet, trying to basically not keep the whole system going and not make it fall over. So you've got Kaufman and Aleshko talking about the size and growth rate of the internet. They say that the growth of traffic on the public internet is still about 100% per year, much higher than traffic on other networks. Data traffic in the US will overtake voice traffic around the year 2002. I think they were meant like phone traffic, and will be dominated by the internet. So you can see that in 97, 98, they're predicting they're kind of seeing this, and they're like predicting that this is going to become something quite big. And you've got big data and the next wave of infrastress by John R. Mache in 1998. And he did a presentation for Usenix, which is a nonprofit, which I think they're still around today, and they do a lot of events themselves. And he talks in his presentation, this is in 1998, he was already talking about bakeries suddenly beginning to sell outside the UK and trying to talk about the stresses that would put on their infrastructure and trying to make sure that the data was available. And some of the things that he talked about I thought was quite interesting, because I think that as data engineers, these are kind of the questions that we still ask ourselves today. So to have the data, cannot find it, and trying to understand the data. So in big systems, where is the data? You probably have loads of data warehouse with loads of databases. You need to know where the data is. Cannot create data from outside, cannot have or process data. You need to be able to process the data. Have it but in the wrong place, and the rapid change of data as well. So these are all the questions that we ask ourselves, we're trying to solve every time we work on a project. And that was something that they were already trying to think about in 1998. So as you can see, this is the rate of growth of the percentage of the population that was using the internet. So the green one is the United States. I'm not sure what the rest of them. Latin America is green, Europe is yellow. And this starts from 1990. 1993 is here when World Wide Web became popular. And this is in 2016. And as you can see, the questions I just outlined to you, they were happening. So this brown line is the world. They were happening when I'd say like maybe 1% of the world was using the internet and generating all that traffic. And they were already trying to figure out how to process it basically, and how best to make that data available. So around the late 2000s onwards, is when you get to see the kind of, let's say, like the explosion of technologies that are kind of popular in the field today. Like for example, Hadoop moved to Amazon Web Services, trying to figure out cloud computing to overcome the limitations of on-prem infrastructures. RabbitMQ, Cassandra, Google Cloud, Redis, and MongoDB come 2008 and 2009. 2010, you get Hadoop becomes Hive, Elasticsearch, Microsoft Azure, Datadog. So Datadog, monitoring, Kafka, Flink, Segment. That's what happens in 2011, 2012. Snowflake. Sure, those of you have heard of Snowflake. Amazon releases Redshift, Fivetran. Docker, of course, you must not forget that the wider, it wasn't just, it was trying to also like run the infrastructure as well. Like, Docker comes in 2013. I was quite surprised that Apache Spark only came in 2014. It just seems like really recent to me. Airflow, Jupyter, and dbt kind of rounding it up quite recently. So I guess all these technologies will begin to pop up, and then you need to, who's gonna it was beginning to get a bit out of hand in terms of like, who's gonna, because all these technologies, they require a lot of specialization to be able to run them efficiently in order to make them run together efficiently. So the definition of a data engineer really comes, I couldn't find the exact date, but early to mid 2010s. The rise of data engineer by, I'm going to butcher this name, but Maxime Beauchamp in 2017. He was the founder of Airflow, and I think this was the first kind of attempt outside the Silicon Valley to try and define what a data engineer is, and in it he says that he observed a growing consensus on the definition and the establishment of what a data engineer actually was. So the growth of data engineer continued. So I went onto LinkedIn, and LinkedIn has this kind of, I think it's an annual report called Jobs on the Rise. So this is a 2023 report. So as you can see, the data engineer is very, very prevalent. It's very, very in demand at the moment. So data engineer is 3rd tech role and 13th overall in the list in the UK of 25. It's #1 role in Switzerland, if anyone of you fancy a move there. Data engineer that appeared in list of fast-growing careers in 24 out of the 28 countries that report went over. So as you can see, we're very in demand. We're very sought after. And I think it's just something that's just the demand for data engineers is just going to continue to grow. And this is where this group comes in, is because I felt like we didn't have well, we did, but I just wanted to create a community for data engineers to come together, because as you can see, I felt like we were a very underrepresented group, at least at the time when I looked at meetups and tried to find a meetup to turn up to. So of course, I could talk about it all day, but let me just bring you an example of online shopping. And that's an example of an industry that's just gonna continue to grow, and continue to generate bunch of data points that we're going to have to be managed by someone. Who's to do that? Who are you going to call? Data engineer. So as you can see, that this graph just shows the popularity of e-commerce in the US. I'm not sure what's happening here. It's a bit flat there, but as you can see, the trajectory is just, I found all the trajectories, whether it's to do with internet, whether it's to do with e-commerce, everything's just has this straight trajectory forwards. And I don't know, I guess I used online e-commerce. Yeah? Oh yeah, it could be COVID, but you'd expect it to go up, not sure. Yeah, but it's just gonna continue to go, oh my God, sorry. Fat fingers. So according to Forbes, 24% of retail purchases are expected to take place online in 2026 worldwide. So the way that companies are trying to sell you is changing. $992 billion was used to advertise the social media platform. $360 billion in sales occurred on mobile phones in 2021, and that's expected to grow to $710 billion by 2025. So I just want to show the growth of the industry and just the amount by how much it's going to grow. And it's going to generate loads of data points that we as data engineers are again going to have to manage and work with and try and make available. Yeah, that's just the graph representing that. Oh yeah, and stuff like Black Friday and Cyber Monday, those things that are becoming more and more popular nowadays, and they bring with themselves their own kind of infrastructure challenges in terms of being able to accommodate that burst of traffic in a very short time. But then again, you're not going to have a massive server that you're then running the rest of the year and paying for. You need to know how to expand and contract with that demand. So that's another example of what's the challenges that we may face. And I just thought this was quite interesting. I went into Google Analytics. I think it's called Analytics. What is it? No, Trends. Trends. Yeah, Google Trends. And I thought, well, is anyone actually looking for data engineering and data engineer? And what I found was that the blue is data engineering, and people were searching for like 2004, as early as 2004, and that was kind of normal, like steady, and then it kind of begins to rise up in like the mid 2010s to 2020s. And data engineer, which is represented by this red line, it just shoots up, and it's right there. And I wanted to compare it for MLOps to Python developers and MLOps, because there's already 2 competing MLOps groups that I know of, and they're not gaining anywhere near the numbers that data engineers are, and yet they have 2 meetup groups and we have none. Well, now we do. So since this is a very new group, I would also like to take this opportunity to remind people of the code of conduct as well. I'd like people to respect others, do not belittle others or their lack of experience. Include everyone, so if you see someone kind of hanging around by themselves, please try to make them feel included. Keep it appropriate. And if you see something, please reach out to either me or my co-organizer Luke anonymously if you do have issues or you see something that you do not like. We need speakers. So please, if you yourself want to have a go, or if you know someone who has done it before or who would like to have a go, please have them to reach out to me or Luke. There's a form that's on the Meetup currently that you can fill. Yes, thank you. Or reach out to me and Luke directly on Meetup, or we're gonna share maybe the email, but we would prefer if you go through the form. Thank you. That's the end of mine. And I think the data WeShape would like to say a few words while we get our next speaker, Luke, set up. Thank you.
Hello. So yeah, you obviously saw me down in reception. I only do that from 7 PM, about 5:30. The rest of the time I'm working with WeShape, and what we are, we're a technology consultancy. We specialise in the advisory and implementations of DevOps, software, data, and cloud native solutions. So the reason this has come up today, I appreciate a lot of data engineers in the building. We have got quite a number of projects in flight at the moment, so I won't bore you with the details so much now. If you are interested in your next project venture, do reach out to me at the end of this. I'd love to have a conversation with you and have a beer or a pizza. Thank you very much.
That over there. Okay. We can go. All right. All right then. We have technology. Excellent. Okay. So just going to try and find out where my mouse is. Okay then. Will this work? Yes, it will. Okay, cool. So I'm going to talk to you guys today about microservices and APIs for data engineers. Yeah, there we go. So a couple of sections. What are microservices? Should you use them? And roughly how you build them. I tend to actually talk more about teams than how, but there we go. We'll get into all of that in a minute. Cool. So who am I? I'm Luke. I'm a consultant here with the WeShape guys. I'm not a data engineer actually, but I'm a DevOps consultant, a SRE, a developer experience guy, architecture. I set up teams. I have led data teams before, but not being one, which is fun. But yeah, so that's me. And what else? So microservices. So what are they? I'm going to adjust this because I want to reach a bit better. Here we go. Yeah. Right, so what are microservices? They're a particular way of designing software applications independently as suites of independently deployable applications. This is Martin Fowler, a really clever honcho in, I think he's in ThoughtWorks at the moment, but this is way back when he wrote this like years and years ago. Microservices have a couple of different ways people will refer to them. Some of them will say APIs, although it's a little bit of a misnomer. They're more like just an interface to things, not the whole microservice. But they could also be called distributed systems. So, they're not just things that your boss says, we should do this, They're a bit more than that. So if you think back to old-fashioned times, you get like monolithic applications that have a set of business needs, and they build some modules of functionality into them. They talk to some kind of storage of data, maybe read it in, and then they fudge around with it internally maybe. They spit it out into databases, and you have lots and lots of different data feeds and different API endpoints, and it's monolithic. There's lots and lots of things all internally. Then you have some change requirement come in. You go, right, we want to switch out to using some other kind of data store. But the requirement is actually only coming from one of the business needs. It's not coming from everywhere. So what do? We go, let's carve this up a bit. Let's go from one place where everything is to several smaller places that can independently change things, can scale independently, and all that kind of stuff. So yeah, should you use them? Well, you probably do already. If you're doing data engineering, you're probably using them. You know, if you think about a data pipeline or a set of them, right? You've got your business need or your data job. Maybe it's an Airflow job, maybe it's a Lambda, who knows what it is. You could take a stream in, could be reading from buckets or databases or all sorts of things. Spit out reports, spit out destination data. Thing is like, they are kind of microservices in those groups already. They're kind of input, process, output, or storage. So each one of those is its own kind of microservice. And it's a distributed system, isn't it? So these is how these sort of definitions fit together. Why are they good? Well, they're good because they isolate the last radius. If something goes wrong, only one of them goes wrong, not all of them. If you change something, a change won't impact all of them. It'll only impact one of them. The code bases tend to be simpler, which means the lead time to change is simpler and quicker. You can get a sort of a velocity out of those things that's better, iterating more quickly. And then you have separation of ownership. It allows you to sort of isolate business functions out to separate teams, which don't all have to collaborate within one big monolith and have to know how all the ins and outs of that entire monolith work. And then independence of architecture. Like we said, you can swap out pieces, use something different if you want. You don't have to use all the same stuff. And its downside, there's a little bit more overhead around backups and ownership, and the ops overhead and the deployment complexity and communication complexity and and then you end up with lots more technologies to understand, like Annie was talking about, 50 million different databases, stores, query engines, who knows, all sorts of stuff. That was in a data engineering career. Now this is completely arbitrarily my opinion and not a hard one either. This is just sort of 3 levels I kind of think of when I think of data engineers. You start off with people who are focused on building a model, outputting reports, just focused on the sort of I have data, I convert it into readable information kind of roles, and they're focused on or just little sort of like preparations and things like that. So it's the early days when you're just getting your feet wet in the water, and then you get a bit more advanced and you kind of go, right, I'm going to start thinking in pipelines, thinking I have data, I need to move it, how do I do that, and getting to know sort of more in-depth technologies, learning a little bit more about how do I spin up new resources in the cloud or on my infrastructure. And at the top level you get big architecture decisions, people thinking, how am I going to piece together lots and lots of business requirements? How do I take a business requirement and turn it into technology? I've put like Java, Spark and Apache there, and it's just like examples of bigger scale systems that tend to be more involved than some of the other tools that are at the upper level. I often think the upper level and more modern tooling is something that people use because there's a lower barrier to entry. They're engineered for simplicity, approachability, and often that means that at an earlier stage of a business or in a smaller scale operation, you can adopt them quicker. When you want to go to something like Spark or Hadoop or all the rest, there's just a much bigger overhead, a much bigger initial investment. So you really have to need it. You have to be at a point where you actually need it to go to it. So what are we going to talk about here? We're going to talk about that middle level really, which is like what are the sort of thinkings around just how do I go from A to B? How do I piece together different pieces to make them all talk? I'm not going to go into specifics of technology. I'm really just talking about philosophy or principles here. So sort of along the same lines as what I just said, it's like this sort of continuum of maturity of a data operation. So we've got like, I swear to God, that's tortured eyes. There's some very tortured eyes right there. That's a man who is depressed. He hates life, and he's taking Excel sheets, manually processing them, and spitting out reports because that's what the business needs. But then you kind of go, right, let's level up a little. That's at the maturity level of baby eating crayons. That's the idea there. So the next piece is like, okay, let's get a bit cleverer here. Let's talk, pipelines. Really, let's talk about pipelines. So we've got a little bit of a distributed system now, haven't we? We've got separate pieces of software, separate responsibilities and roles, separate problem domains. but all kind of working within a collaborative infrastructure. I've almost built like a sequence of steps there, isn't there? It's like, you know, your cloud data is pulled in by a Python script, dumps it to a bucket, and then the bucket gets used to process it into organized information in the database, and the database is queried by something to spit out reports. And obviously, probably DBT is the wrong tool in the wrong place there, but anyway, we'll not think about that. Yeah, so that's sort of like, we're getting a bit more of a smart monkey here, aren't we? Next step, a much more comprehensive data estate. Something that involves all sorts of phases and interoperability and distribution of problem solving. You know, so think of like ingestion happens, data tiers go through the medallion phases of you know, maturity. You have a processing engine set of principles that have to be worked on, and event streams that are triggering these things and being fed both metrics and applications feeding events into that are processed, stored, reprocessed and analyzed, put out reports and analytics engines, made available to ML processing, used by external users and internal users alike. You get the whole thing. It's like a whole sort of life cycle of data and a kind of a complete sort of ecosystem in a way. Yeah, so that diagram took way too long to draw. So, you know, we're some pretty cool cats at this point, right? So, where do we go from here? What did I have to do twice? Oh, I think I had 2 copies of it. Oh, well. So, one of the things I think about in this diagram is we're not just talking about pipelines. There are pipelines in there. There are microservices, which are data processing systems. But we also have a load of APIs. We have things that are receiving events. We have applications that are processing stuff out of data stores. We have and emitting their own information. We have APIs that are collecting information and events, storing them into your data tier, data lake to be later dealt with. So you have all this API stuff, and that's the stuff that sometimes you think this is just the domain of the software developers. You know, data engineers, do we do this? I hope so. And that's where, you know, okay, microservices are one thing. So APIs is why I mentioned at the very beginning, is a part of it. Maybe it's a subset of microservices. And it usually comes down to a thing. It's like, is it an event or is it an API? And the decision around this kind of comes down to synchronous or asynchronous or batch operations. You know, if it needs to be synchronous, you probably want an interface that you call and an event transactionally happens. Asynchronous is like, there is data and something picks it up eventually, processes it and sticks it somewhere else. That's an asynchronous process. That's something that's or a batch process. These things are kind of like good deciding factors, good principles to sort of make a decision. Which do you actually need to turn to? Use cases, right? So, you know, APIs are great for querying data, exposing the data you've collected, dealing with the I can see my own slides finally. I just figured out how to use presenter mode properly. Yeah, so you've got you've got your data sets that are exposed through an API, so people can then query and filter and, you know, inspect that data in a programmatic way, and, you know, properly integrated sort of processes. You can collect data. Yeah, you've got endpoints that maybe are just pure ingestion points. People are posting stuff to you. So people are sending you events or blobs of information, and you're consuming them. Your apps are collecting them, and then you want to store them down, as well as deal with them in the business logic separately. But these are all things where data engineers get involved and say, well, we need to know how to deal with all these APIs and how to actually architect for this sort of area of problems. This is why I think it's an interesting discussion to deal with. Triggering events. You know, you have an API which allows you to do orchestration of events. You can say, okay, I can build an API that actually lets me trigger my batch jobs, trigger my ingestion events, or trigger some kind of report generation, whatever it might be. And then, of course, machine learning. So, you get like APIs which are wrapped around models that allow you to do inferences. So you can actually get insights out of your machine learning models. And of course, parameterized training batch jobs, again, it's really just like triggered events of a different type. So why use an API? So I mean, like I said, data engineers are building models, analyzing and producing good information. And then of course you have to gather the information, or you have to make it available to others. So you need an interface. That's what an API is. It's an interface. It's a way to say, this is a structured way, organized way, contractually organized or documented way for you to talk to the data, rather than it being overly exploratory and free form like a notebook tool or something. So that's kind of the how and why. So let's talk a bit about doing it. So building up microservices, let's talk about architecture patterns. How can we put these things together and achieve some of what that crazy diagram earlier looked like? So we have simple things like database pattern. Is it a shared database? You have your applications all talking to one database. It makes it simple, consistent. You can do ASP compliant transactions, and data set queries are easy to mix together. And excuse me, ooh, getting dry mouth already. And then on the con side, tightly coupled to your applications, a little less flexible, especially if everything's using all the same data schema. Cross-application domain interference. Yeah, this is the idea that you have one schema, one database set. You change something, but someone else is relying on the same one. Oh no, you've got like issues between the two sets. It's a bad pattern in a lot of cases, especially as things grow and get more complex. And it's a single point of failure. That database goes, oh my god, several services are down, not just one. So that's why we talk about a decentralized pattern. It's just take the database, separate it out, so each one only has its own database. What's good about it? Loosely coupled. Everything is independent. And blast radius concerns are gone, or minified, reduced. Yeah. Downside, joining across data sets, a little harder. Increase in operational overhead. Yeah, there's a little bit more work to manage the separate set of databases, isn't there? And then of course the separate capacity planning and FinOps, it's like, we have to account for more databases or more separate sort of instances of everything, and everything has its own capacity calculation. And so we need an aggregate kind of like analysis of all that ongoing, rather than just having it all in one place and kind of grow one big blob of storage. That's a bit easier and simpler to think about. But I think the pros outweigh the cons, in my opinion. Anyway, what else have we got? So composition pattern. This is one of these ones where you go, I've got an API, but I have several APIs, but I only want one endpoint. So let's do something about that. Let's put a function in front of it. You call your load balancer or your proxy or whatever it is. It calls think lambda or FAS or something like that in the back end that does a load of routines and calls out to other subservices and orchestrates that together. A different bunch of result sets, maybe passing parameters from the results of one into the other. And allows for diversity of jobs, APIs, things that are talking to streams versus databases, lots of different variety there. It's a simple unified client, can span multiple business functions and separation of concerns. So yeah, everything is like nicely isolated, nicely pulled apart. The downside, it can be slow. That's the big one really for me. And of course, that function or that load balancer becomes a single point of failure across a whole bunch of stuff. Or one application failing breaks the chain, and suddenly related parts of the result set can no longer be served. Even though
like GraphQL function.
Oh yeah, that's exactly what it's like. Yeah. So there you go. That's actually a really good point. GraphQL would be in exactly that kind of idea. Although I like the idea of a function, because it means you're sort of like separating out in an almost like a messaged way what's happening. But yeah, it's an interesting comparison. There's different ways to skin the cat, isn't there? So what's another one? CQRS, separation of read and write. There's one of those real typical ones you see in database read, write, master kind of sort of setups. And it's really just you have the load balancer separating the different verbs or actions that are coming into your API, saying let's write to this instance, but only read from the other one. And that allows lots of good things, like, again, separation of concerns. So writing and reading as concerns are separated. If write goes down, you can still read. Your app isn't down. Just part of its functionality. Independent of scaling, so if your writes are quite quiet but your reads are absolutely blazing, then you can replicate the heck out of that data set or those API instances and scale them independently. Cons. Data replication latency. You've got one of those things that happens, which is, I wrote data, but it hasn't shown up when I read it again because something broke, or it's just overloaded. Who knows? And then, of course, you get implementation duplication, which is like, I've rewritten API endpoints to do two different sets of operation, but I've just spent time doing both twice. So yeah, and more complexity. Obviously, you've got the orchestration or the corralling of the replication of the data sets and all that kind of stuff. Again, one of those things, if it suits your needs, it's great. Event source pattern. I think this is kind of the pinnacle. This is kind of like, where the most modern and advanced data structures come in. You have a mixture of, well, really it's just like, it's all about event streaming, isn't it? You get an API, it writes an event onto a queue, and you just get a confirmation saying, okay, event stored. Was it 202? Process later, or whatever it is, the HTTP result. So that goes onto a message queue, and then it can be queried in a read endpoint. So you kind of have to implement CQRS to do event streaming, which is interesting. And the good size of that, separates concerns. I always say that. I always say separate concerns because I really believe in domain separation. So it supports the concept of materialized views as kind of built-in capability. You process the data after the message has been submitted to an event. And guess what? You can always reprocess your materialized view over and over again. And that means that your view can change over time if you need it to. Also, your sort of ability to replay is built in and audit. So this is like a combined thing. You can take those messages, send them off somewhere else, or re-request them. And they can be put into separate data stores, analytics engines, reprocessed by some other processes for other purposes. Anything really, an incredibly powerful element of the architecture. Downsides, consistency of data. You're creating a really, really complicated scenario here. But that's where the next slide comes in. And again, more complexity, and the learning curve gets really high at this point. You've got to have a lot of skills come to bear. You have to have a lot of expertise in your team and all the rest. But anyway, data consistency. What do we do about that one? Because that's a big one, right? Saga Patterns. Saga is a whole world of fun. It's it's one of these things where you take data sets and you allow a sequence of different events or processes deal with the life cycle of the data going through the system. You think, I want to create a purchase, say, the example I've seen actually is bank. Bank is a good one. You go, right, I want to make a transaction in my bank. Right, so what you do in an asset compliant system, you just go SQL, open transaction, get account, check balance, is it high enough? Great. Decrease money, send money order to somewhere else, commit transaction. That's great, isn't it? And that's got rollback all built in, it's lovely. But it's not very what's the word? Cap theorem, available. Consistency, availability, and P? Partition. Let's forget that last one. But it's available. It's consistent, but it's not as available. You get sort of a contention, contention resource there. The row is only available to so many processes at once. So you want to have a system that goes, well, I want to have a bank transaction go in. What do? First thing, retrieve data on the account. Right, and then check some kind of limits. If that's approved, we create a transaction object. Next thing, we have to take the money out. But we have to recheck that it hasn't been closed already, or that the money hasn't gone off somewhere else already. So every step of the transaction, you're kind of checking constraints. And that's like a way to say, let's stop any data inconsistency creeping in, or allow for rollback if the transaction needs to be interrupted. There's two ways of doing it, orchestration or choreography. So the orchestration is, you have a central agent that knows the sequence of steps that have to happen, and it goes off and says, call this one, wait for the result. If it's happy, call the next one, wait for the result. If something goes wrong, roll back those. So it knows what's going on. It's a central organizer. The other one is choreography, where one message is consumed by the next process, and there is metadata about the sequence of events in the message that allows you to make decisions on whether or not this should keep going on. So the message comes out of service 1, service 2 picks it up, looks at the metadata of the events and decides what it needs to be able to do, and then can say, oh, I'll do that, and then it adds a new metadata set to the next message. So service 3. That's going to sound great on YouTube. So that's like the choreography pattern, What's good and bad about this stuff? Maintaining data consistency. I mean, it's just get that consistency along with availability, please. Rollbacks are possible, and clear separation of concerns. Again, it's a set of microservices to do one thing. Each Saga is a step in, each process is a step in the Saga. Isn't that right? I always forget actually what the rule is, but I think it is. Yeah, I think it's like each step in a Saga is a separate microservice in its own right, because it's its own set of problem domain that it's solving. It's like check that things are okay and open a transaction record, deduct money from an account, and then validate that the transaction has been done successfully. Look at that. That's a set of like constraints separated out into two separate steps, two separate microservices doing each of those steps even. They just could be batch jobs, things consuming messages off a queue, whatever it is. So, great. Downsides. Again, big whole learning curve. It's always a big one. And the underlying complexity is pretty high. You have to understand these principles. And debugging. But then, we get into the wonderful world of modern tracing and all that kind of stuff. So, but we won't get into that too much. So, if your brain is melting, I'm sorry. That was a lot to go through, wasn't it? So, how on earth do we do all this? Thankfully, take this down a notch, shall we? You have to build a team to get this done. Who do you need? The gang. You got to get the people together, people who know how to do it, and gets things done. So you need a bunch of skills. Now, this is just my thoughts around what a skill set distribution looks like. It's types of skills you have. You need people with the data engineering skills, the operation, DevOps, that infrastructure side, API developers, people who are maybe specialists in software, not necessarily also not engineers. Sorry, data engineers. I can't say that straight. Yeah, people who can write software. Maybe they're data engineers, maybe they're specialist software developers. Could be either. And business domain people. People who understand the business you're in, the industry, the business problem, whatever it might be. So you need to have this mix of capabilities coming together. How you sort of split all this up, I don't know. Here's an example of one way to think about it. We've got the business stakeholder, the data engineer, and the infradev API all mixed together. So, and you kind of go, this is like a team needs to have a combination of these things. I can go into those points later. I don't know. How am I doing time-wise? 25 minutes in, I'm doing okay. How do you sort of break this apart into the people in the team? You have a team which everybody's got their own little specialization and they have to collaborate really tightly to figure out how they can all work together. Or you have the technical side really together and the sort of maybe business domain separated out so that they're more like external stakeholders, as they say, the chicken to the pigs, if anyone knows that little anecdote. Does anybody know that anecdote? Oh, okay, I'll tell it. All right, so, you got the chicken and the pig having a conversation, and chicken says to the pig, I've got this great idea. The pig goes, what's that? He says, let's open a breakfast restaurant. And the pig goes, oh, I don't know about that, man. Yeah. So what do you mean? Chicken says. And the pig goes, well, I mean, I'm invested. You're just involved. Because the pig has to give you bacon. The chicken just gives you an egg. And the idea is that people who are committing all their time, absolutely invested in doing the work, are the pigs. We're engineers, we're the pigs. People who are business owners, they just set a bunch of requirements and let you go off with it. They're the chickens. So that's how that actual anecdote works. Right, so, and then so separated people, technical focus maybe is one other arrangement, or everybody is a bit of a crossover and specialist. You got a data engineer who knows APIs and also understands the business you're in. Oh my God, bloody unicorn. So there's kind of which arrangement of people do you need to find? And then, some of it will to do with the topology of your team in the business. How are you arranging your teams? Are you a center of excellence? You got this falls under, I find as well, the tribes and squads concept, where you have people who all sort of share discipline, are embedded across a bunch of teams, but they have a central organizing point or a get together or whatever it might be, some way to share ideas, share practices, set standards for each other to share around. And it's good. Good for the sort of mid-sized organization, I find. and yeah, it kind of creates cohesiveness, a standard of practice, and hopefully, a good sort of consistent and standard way of operating. The centralized method, super centralized, super consistent, everything is standardized, but the response to teams' requests and things like that can be a bit slower. It's good in a very mature organization where you maybe have very strong platform engineering and business and management and things like that, and the business functions are well isolated and well staffed. Then you have the capability to act as a centralized team. But if you need more speed and agility, you go decentralized. Better in early stage businesses, or people are going through big change all of a sudden and they just need to allow teams to pivot and be agile and flexible about whatever they're doing. And the sort of distribution of skill sets might differ in each case. With a highly decentralized team, you may need a team that has all the skills. You need somebody who's got like business domain knowledge and the data engineering and infrastructure knowledge and software development knowledge all together, and then everything in between to the super separated out skill sets. The DE people just know their data engineering principles really well. You've got platform engineers who take care of the tech for you, and you've got the business teams who know the business stuff really well, and separate API developers who swoop in and just write you an API when you need some certain requirements, whatever it might be. So yeah, it's a sort of a continuum of things there. There's probably way more topologies, and if you want to know more about topologies, I mean, just go read the book. It's a good book. Yeah. And that is kind of it. That's my talk. Thank you very much for your attention. Any questions?
Questions?
No? I think we're all brained out, aren't we? Okay, cool. So thank you very much. We need speakers, I'll say it again. You can find me on the internet a little bit, although I post very little, so you probably won't find much from me. And yeah, thank you to WeShape again for setting all this up. And Annie.
So anyone who's interested, we're going to be going down to the Lehman Tavern in a couple of minutes. So if you would like to join us there, you're very welcome.
Great stuff. Thank you, guys.